In this video, let us learn one important, quite interesting topic called arborescence. We know what is tree in case of undirected graph. It was defined as a connected graph without any circuit. Like in connected graph, we define tree as a connected graph without any circuit. The basic concept as well as the term tree remains same when we come to digraphs. A tree is a connected digraph that has no circuit, neither a directed circuit nor a semi-circuit. So a tree in digraph, okay, a tree is a connected digraph that has no circuit or no cycles. No circuit, neither a directed one nor a semi-circuit. Neither a directed circuit nor a semi-circuit. Okay, this is how we define tree in case of directed graph. And of course here also tree of n vertices will contain n minus 1 directed edges. Trees with directed edges are of greater importance in many applications such as electrical network analysis, game theory, computer programming and some counting problems, etc. So in addition to being trees in the undirected sense, trees in digraphs have some additional properties and some variations resulting from the orientation given to the edges. One such particular useful type is nothing but arborescence. In fact, it is a rooted tree with directed edges. Okay, so let us learn about arborescence. Arborescence, a digraph G is said to be an arborescence if G contains no circuits. It means neither a directed circuit nor a semi-circuit, and in G there is exactly one vertex of 0 in degree. Okay, it's a digraph and it has got no circuits, neither a directed one nor a semi-circuit, and there is exactly one vertex of 0 in degree. So I'll explain with an example. See, this is an example for the arborescence. You can check this has got no circuits, neither a directed one nor a semi-circuit, and there is only one vertex of in degree 0. This is the vertex. In fact, it's a root. We call it as a root whose in degree is 0. Every other vertex has got in degree, and in fact, in arborescence, only one vertex is of in degree 0 and every other vertices are of in degree 1. Okay, so when we define it as arborescence as a directed graph without any circuits and there is exactly one vertex of in degree 0, we can even define it as a digraph in which for a vertex say called root, say if I call it as u, then any other vertex, say any other vertex, I can take this or this, for any other vertex v, there is exactly one directed path from u to v. My v vertex v can be here, can be this, can be this, can be this. So arborescence is a digraph in which for a vertex u called root and any other vertex v, there is exactly one directed path from u to v. This is the other way of defining an arborescence. As I mentioned earlier, an arborescence is a tree in which every vertex other than the root, has in degree of exactly 1. Let us prove this. By looking at the arborescence itself, we can say that it is a tree. But the thing is, arborescence is a tree where every vertex other than the root has got in degree equal to 1. So when I say arborescence has n vertices, okay, if arborescence has n vertices, then it can have at most n minus 1 edges, because of the condition 1 that says that it is this digraph is not containing any circuit, means it is not having any directed or semi-circuit. So since it's circuitless, a graph with n vertices can have at most n minus 1 edges. Therefore, when I take sum of all the indegrees of these n vertices, then that must be less than or equal to n minus 1. Since it's circuitless, graph G, suppose I'll consider this. This has got n vertices, and since it is circuitless, it can have at most n minus 1 edges. Therefore, sum of all the indegrees of all these n vertices must be less than or equal to n minus 1. So d minus of v1, v2 like that, d minus of vn, sum of all in degrees must be less than or equal to n minus 1. Now, out of all these n vertices, only one is 0. Only one, and either this or this, any one. One is 0 because it is mentioned that by the definition of arborescence, we know that it has got only one vertex of in degree 0. So among all this, any one is 0. Out of this, one vertex has got in degrees 0. Therefore, of these n terms on the left hand side of the equation, only one is 0 because of the condition 2. Because of the condition 2. That says there is exactly one vertex of in degree 0. Okay. So when one term is equal to 0, then the rest must be positive integers. Okay. Therefore, they must all be equal to 1. When I consider, suppose this is the root, v1 is the root of the arborescence, then d minus of v1 plus d minus of v2, like that when I take, minus of vn, this must be less than or equal to n minus 1. If v1 is the root, then this entry is equal to 1. And these values must be positive integer, okay? And they must all be equal to 1. Okay, since there are exactly n minus 1 vertices of in degree 1, vertices of in degree 1, and one vertex of degree of in degree 0. Digraph G has exactly n minus 1 edges. G has exactly n minus 1 edges. Since it's already mentioned that it is circuitless, it must be connected. Therefore, I can say it is a tree. Thus, I have proved an arborescence is a tree in which every vertex other than the root has an in degree of exactly 1. In fact, an arborescence is a tree directed out of a root. See, when we draw like this, it's a tree directed out of a root. So, sometimes we call this arborescence as a out tree. Out tree, since all the edges are directed out of the root. Okay, if I reverse the directions, reversing the direction of every edge in the arborescence, get something like this. Okay, then it is called as in tree. Here edges are directed out of the root and here edges are directed into the root. Therefore, this is called in tree and this is called out tree. Let us look at one more theorem. This theorem is similar to the definition of the arborescence. In fact, it says in an arborescence there is a directed path from the root to every other vertex. Okay. Conversely, a circuitless digraph is an arborescence if there is a vertex V in G such that every other vertex is accessible from V, but this vertex is not accessible from the other vertices. Okay. So let us take the first part. Arborescence. In an arborescence, there is a directed path from the root R to every other vertex. Okay, let us prove this part first. See, let me take a path P, path starting from root R. Okay, in an arborescence, consider a directed path. In fact, directed path P starting from the root R, and I'm continuing this. Suppose this is graph, for example. Okay, from the root R, I'm taking a directed path starting from the root as far as possible. Okay, so P, this path is getting end at a pendant vertex only. If I start from this side and it is ending at this point, which is a pendant vertex. So P can end only at a pendant vertex. Otherwise, we get a vertex whose in degree is 2 or more. You got my point? See, if I have a path P starting from R, this path P, if I take it like this way, then it is ending only at the pendant vertex. If I take it like this, then again it is ending at a pendant vertex. Because if it is not ending at a pendant vertex, then say suppose here, suppose, okay, then it is ending over here, suppose I consider, then it means that there is a vertex which has got in degree more than 1. That will not be a arborescence, right? So P can end only at a pendant vertex. P can end only at a pendant vertex. Otherwise, we get a vertex whose in degree is equal to 2, as I observed, as I mentioned over here. Okay, suppose this edge is there and path is from R2 and it goes here, then it means that one thing is it has got a circuit, so that it cannot be arborescence. And another thing is you will get a contradiction that you have got one such vertex whose in degree is more than 1, right? So P can end only at a pendant vertex. Since arborescence is connected, every vertex lies on some directed path from the root. I know it is connected, so every path, every vertex will lie in some of the other path from the root, right? And it is ending at the pendant vertices only. So I can say that in an arborescence, there is a directed path from the root to every other vertex. Let us look at the second part. It says a circuitless digraph G is an arborescence if there is a vertex V in G such that every other vertex is accessible from V and V is not accessible from any other vertex. So conversely, suppose G has got n vertices, okay? I have to prove it is an arborescence if there is a vertex V in G such that every other vertex is accessible from V, but V is not accessible from any other vertex. See, since every vertex in G is accessible from V, G has no circuit then, right? Suppose this is V. Every other vertex in G is accessible from V. That means that G has got no circuits, right? G has no circuits, neither a directed nor the semi-circuit. So it has got no circuit. That means G is a tree, right? Now it's mentioned that V is not accessible, other vertex is accessible from V, every other vertex is accessible from V, and V is not accessible from any other vertex. Therefore, I can say V is not accessible from any other vertex. Okay, therefore I can say in degree of V is equal to 0. But every other vertex is accessible from V. Therefore, in degree of each of these vertices must be at least 1. I'm so sorry. It's mentioned all vertices are accessible from V, right? Therefore, I can say that suppose this is my V for this graph. Every other vertex is accessible from V. Therefore, I can say it has got no circuit. Therefore, it must be a tree. Now, it's mentioned that V is not accessible from any other vertex. Therefore, in degree of V must be equal to 0. And every other vertex which is accessible from V, every other vertex which is accessible from V, the in degrees of all these, each of these vertices must be at least 1 in degrees of, say, this V1, V2, V3, like that. Then in degrees, since V is not accessible from any other vertex, if I take any other vertices other than the V, they have got degree at least, once again I'm writing like that only, at least 1 in degree cannot be greater than 1 because there are exactly n minus 1 edges in G. N being the number of vertices, therefore it has got n minus 1 edges. So there is one vertex of degree 0 and every other vertex has got in degree at least 1. So the in degree cannot be greater than 1 because of this condition. Therefore, I have got one vertex of degree 0 and every other vertex is of degree 1. So that graph G becomes an arborescence.